Okay, so in this video, I'm going to cover just some more of section 10.2 and 10.3. Remember, we're combining those two sections together there. We're on problem 18. We've done problem 17 and problem, like all these other problems here. So remember that a permutation and combination are both where an object cannot be repeated. And with a permutation, order matters, and with a combination, order does not matter. Okay, we did problem 17 there. So problem 18 says, how many different 5-member committees could be formed from the 100 U.S. senators? Okay, so they're not talking about positions or anything like that. They're just, a group of 5 people, which means that order is not going to matter. Okay, so there's 100 senators. We need to choose 5 of them. So 100 choose 5 would be what I'd type in there. And by the way, so for these problems, I was showing you how to do the calculation using the formulas. I'm not going to be as picky about using the formulas here. So just of course, make sure that you've recognized whether or not you've got a permutation or combination, and then the answer is correct. Okay. We have 100 choose 5. 100 choose 5 is 75,287,520 committees. Okay, so that's how many groups of 5 are possible from the 100 U.S. senators. Okay, problem 19 says the school musical director can select 2 musical plays to present next year. One will be presented in the fall and the other presented in the spring. If she has 9 to pick from, how many different possibilities are there? Okay, so if she presents one in the fall and one and a different one in the spring, and you flip those, you're not saying the same thing. Okay, because the one that was done in the fall is going to be done in the spring. The one that was done in the spring is going to be done in the fall. That's not the same thing at all. Okay, so the idea here is for us to recognize that we got a permutation, order matters. There's Remember, the fundamental counting principle could be used in place of permutations. Okay, so I could lay out 2 spaces. I'm going to present 2 plays, one in the fall, one in the spring, and I got 9 possibilities in the fall. So all of them are possible in the fall, right? And you're not going to do the same one in the spring that you've done in the fall, right? Because everyone's seen it. So there's going to be 8 possibilities in the spring. So 9 times 8, that gives you 72 possibilities total. Okay. Problem 20. A newspaper editor has received 8 books to review. He decides that he can use 3 reviews in his newspaper. How many different ways can these 3 reviews be selected? Okay, so you got 3 reviews going into the newspaper. It's not going to matter the order that that those 3 plays are done. Okay, or book reviews are going to be done. Okay, so because we're not interested in the order there, combinations would be the option to use there. You got 8 books. You're going to choose 3 of them to put in the paper. Okay, 8 choose 3 gives you 56. Okay, so there's 56 different ways that you can select the 3 from the 8. All right, I've got the homework in section 10.2 and 10.3 given there. I've got several more problems here to look at. These are just some more practice problems for us to consider. Now, the idea is that these problems will get tougher as we go along, so keep that in mind. But the idea, of course, is for us to identify what technique to use and then use it correctly. Okay? Let's take a look at problem 21, where it says a man has 6 shirts and 4 ties. Assuming that they all match, how many different shirt and tie combinations can he wear? Okay, now even though I'm saying the word combination, that doesn't matter. Okay, so how many different ways can he select one shirt and one tie? Well, he's got 6 shirts. He's going to select 1, and 4 ties. He's going to select 1. 6 times 4 is 24 outfits. The end. Okay, but by the way, for this section, sometimes students, for whatever reason, think I'm asking them some crazy multiple step combination type problem where all they had to do is multiply 2 numbers together. Okay, so be aware of that. Okay, permutations and combinations, by the way, should be a Plan B option, not a Plan A option. Okay, a Plan B option. Okay, so keep that in mind. The first thing that we should always be thinking about first is if we can use the fundamental counting principle to do the problem. Let's take a look at problem 22, where it says that a pizza place offers the following toppings for its pizza. Sausage, pepperoni, ham, onions, mushrooms, olives, and peppers. How many different pizzas are possible if the pizza contains 1 meat and 1 vegetable? Okay, so I'm selecting 1 meat out of the 3 and 1 vegetable out of the 4. Okay, so 3 times 4 is, there's 12 pizzas that are possible where you're going to have 1 meat and 1 vegetable on them. Okay. Problem 23. A lock has a dial with numbers 1 through 30. To open the lock, you must turn the dial to 3 numbers in a specific order. How many sequences of 3 numbers are possible if all the numbers are even? Okay, so, on this lock, you got 30 numbers, so half of them are going to be even, half of them are going to be odd, right? So there's 15 even numbers. Okay, now they didn't say anything about not repeating. So you could have one possible combination to consider there could be 8, 16, and 8. Okay. Well, there's 15 numbers that are even. Okay, so go to one of the 15 numbers. Now, again, it did not say anything about order not repeating or anything like that. Okay, so all 15 numbers are available for us for the second number. Okay, so go to one of them for the second number. All 15 numbers are available for the third number, so go to one of them for the third number. 15 times 15 times 15 should give you 3,375 different sequences or groups of 3 numbers that are possible. Okay. Problem 24. A social security number is used to identify each resident of the United States uniquely. The number is of the form given there, where each X is a digit from 0 to 9. How many social security numbers can be formed? Okay, so 0 to 9, that's 10 digits. Okay, and the first one can be a 0. They didn't say anything about that. So I've got 9 different X's, and in each one of the 9 spaces there, I can have 10 digits. Well, that'd be the same as 10 to the 9th. Okay, 10 to the 9th gives you 1 billion social security numbers. Okay, by the way, just as a note, the U.S. population in the year 2017, for example, was 325.7 million. Okay, so we're quite a ways away from 1 billion social security numbers. But if we, whenever we do reach 1 billion, we're gonna have to change the way that social security numbers are formed there. Maybe we add another X or whatever. Okay. Problem 25. You've just been hired as a book representative for Pearson Education. On your first day, you must travel to 8 different schools to introduce yourself. How many different routes are possible? Okay, so you got 8 schools. Well, you go to one school. There's 8 possibilities, right? And then now, once you've been to a school, you're not going to go back to that same school. You've already been there, right? So 7 schools remain. Okay, go to the one that's 7. and then 6 schools, go to one of the 6, and then 5 schools, go to one. Well, that'd be exactly 8 factorial. 8 factorial, using your calculator, gives you 40,320 different routes that are possible. Okay? Problem 26, and by the way, notice how all of these problems are nothing about permutations and combinations, okay? But problem 26, all we know about Shannon, Patrick, and Ryan is that they have different birthdays. If we listed all the ways that this could occur, how many would there be? Assume that there's 365 days in a year, so we're not dealing with a leap year or anything like that. Okay, so the easiest way is to use the fundamental counting principle. So there's 365 choices for Shannon. Pick one of those days. Now, Shannon, Patrick, and Ryan have different birthdays. Okay, so there's 364 choices there for Patrick. Pick one of those days. And 363 choices there for Ryan. Pick one of those days. Okay, so 365 times 364 times 363 should be 48,228,180 different ways. Another way that you could do this is you could think of this as a permutation. Okay, order is going to matter. So let's say Shannon's birthday is on November 8th, Patrick's birthday is on October 22nd, and Ryan's birthday is on February 4th. Okay, now if you switch Ryan and Shannon, does that mean the same thing? No. It doesn't, because now Shannon's birthday would be on February 4th, and Ryan's birthday would be on November 8th, right? So it's not the same thing at all that you were saying previously. So order does matter here, which means that we should be thinking about this as a permutation, not a combination. 365 permute 3 gives us the same result, 48,228,180 different ways. Problem 27 says, suppose that 40 cars start at the Indianapolis 500, and how many ways can the top 3 cars finish the race? Okay, by the way, a race is a classic example of a permutation. If you have the car that wins the race, is that the same thing as the car getting second place or third place? No. The car won, right? So order is going to matter. Right? If you look at the first place winner and the third place winner, and you switch those two, it does not mean the same thing. So 40 cars are racing. Okay, well, only one of them is going to win. Okay, and then 39 are still racing around. Okay, choose one for the second place. And 38 cars are racing around, so choose one for the third place. 40 times 39 times 38 should give you 59,280 different ways. Okay. Since order matters, this would be an example of a permutation. 40 permute 3 would also give you 59,280 ways. Okay, and by the way, your book or I, for that matter, it won't care how you do the problem. Okay, so some people are going to use a permutation, and some others are going to use the fundamental counting principle. I don't care. Okay, just as long as you're getting the right number there, that's all we care about. Problem 28 says that a menu in a Chinese restaurant lists 12 dinners in column A and 7 dinners in column B. A family wants to order a total of 5 different dinners, in which 4 will be from column A and 1 will be from column B. How many selections are possible if there are no restrictions on who gets what dinner? Okay, so there's 12 dinners in column A and 7 in column B. Okay, a family's going to order a total of 5 different dinners, which 4 are going to be from column A and 1 is going to be from column B. Okay, so whatever the column B is, there's 7 in column B, you're going to choose 1. Okay, so in column A, you're going to choose 4. Okay, now we don't care who gets what dinner. Okay, there are no restrictions on who gets what dinner. That's important. So combinations would be used. Okay, there's 12 dinners in column A. We're going to choose 4 of them to order, and then times 7 from the column A dinners. Okay, 12 choose 4 gives us 495. If you were to check that, and then times 7 should give us 3,465 different selections that are possible. Okay. Let's maybe do problem 29, and then we can stop. If 4 students enter a classroom that has 10 vacant seats, in how many ways can they be seated? Okay, so if Jimmy's sitting at the back of the room, is that the same thing as Jimmy sitting at the front of the room? No. So order is going to matter, right? Since the order matters about who's sitting where, a permutation is going to be used and not a combination, because with combinations, remember, order is not important. Okay? 10 students are going to, or there's 10 vacant seats, excuse me. 4 students are going to enter in the classroom and sit down. 10 permute 4 gives us 5,040. Okay? Again, we could have used the fundamental counting principle. So you got 10 times, now once a seat has been filled, there you can't sit down there, right? There's 9 open seats. Okay, so choose one of the 9 to fill. Okay, then there'd be 8 open seats. Choose one of the 8 to fill. And then 7 open seats. Choose one of the 7 to fill. Okay, but 10 times 9 times 8 times 7, that gives us the same thing, right? 5,040. So either way, there's 5,040 different ways that they can be seated. Okay, and we'll go ahead and stop right there.